This is the second part of ray diagram. Figure shows a white light which is incident. White light is a combination of all the 7: violet, indigo, blue, green, yellow, orange, and red. The Webgyor, in which violet bends the most and red bends the least. So red light path is shown. We have to complete for a violet. And we have to complete the path for a red, so it will bend away from the normal. So that's, we label one as a violet, another one is a red. Figure 6.1 shows a rectangular glass block. The ray Fe is partially reflected and partially refracted. So if partially, like small amount of the ray is reflected, bounce back from the surface, and small amount of ray is refracted. So draw approximate path of a refracted ray. So when it first it moved from air to glass, it bent towards the normal. And then when we draw the normal, the imaginary line which is perpendicular to the surface. So moving from glass to air, what will happen? It will bend away from the normal. And keep in mind, the ray which incident and the ray which emerge out, both should appear parallel, right? Both should be parallel to each other. So emergent ray and the incident ray should be parallel to each other in a rectangular glass block. And always label them, like here, the incident, this one is a reflected, this one is a refracted, and this one is a emergent ray. Because as I mentioned, draw the path of a reflected ray and label as well. So right here, reflected. Figure 7.1 and 7.2 shows a wavefront of a light approaching a plane mirror. Draw the path to show what happened to the wave at strike. So light strike the surface, so reflection. Imaginary line which is perpendicular to the surface, that is the normal. When the light strike, it changes the direction. We call that as the reflection. So this will be the reflection. And after showing the reflection, we'll draw the reflected wavefront, which are always perpendicular to direction of the wave. So these are the reflected wavefronts. But moving from air to glass, because the speed of the light decreases. So when we draw the normal, the imaginary line which is perpendicular to the surface. So what we'll observe that the speed of the light decreases. So the speed of the light decreases. And then to draw the refracted, it bent towards the normal, speed decreases. And to draw the refracted wavefront, direction of the wave, we just check the direction of wave. So direction of the wave and the direction of the refracted wavefront should be perpendicular to each other, or 90 degree to each other. So this is how we draw the refracted wavefront. So moving from air to glass, speed of light decreases. Moving from glass to air, speed of light increases. So the waves are moving deep region, the water waves are moving fast. In a shallow region, the water waves are moving slow. So if it is moving slow, so the wavefronts will lag. So example, if the wavefronts are traveling with the same speed, then it should be exactly same distance. If the wavefront traveling faster, then we should roll in this manner ahead. But because it is traveling slower, so it will lag behind. As a result, when it will lag behind, when we complete the figure, so it will appear like this. So on figure, remainder of A and B plus the two previous. So remainder and plus the two previous which already passed. So we'll draw a wave in this manner, because moving from deep to shallow, the speed of the water decreases. That's why the wavelength should also decrease. If it was a shallow to deep, then opposite we will draw that the wavelength should increase. Figure 7.1 shows a view from above the water approaching a narrow gap. The water on both sides of a barrier is same depth. So we have to complete the pattern whenever a wavelength and gap size are approximately equal, then maximum diffraction, and as a result of a maximum diffraction, what will happen? Wave will spread out more. Using a compass, you will draw and keep in mind that the wavelength, this wavelength should be equal to what we draw, because the wavelength does not change as the medium does not change. Figure 7.1 shows a principal axis of a converging lens. An object is there 2 centimeter, which is placed 2 centimeter of the left. Focal length is 3 centimeter. So it shows focal length is using a ruler. We'll mark focal length, like example, f 3 centimeter here, and f is 3 centimeter. An object is placed, as I mentioned, object is placed on the left 2 centimeter from the lens. So this is the position of object. We have to draw an image. So how to draw an image formed by a convex lens? It will be an inverted, magnified image, because the object is between the focus and the lens. So first the parallel light ray. First the parallel light ray, it will pass through the focus. One through the optical center will pass straight. The two light rays will never intersect. So what will happen? When our brain senses that the light is coming straight from the object, it relocate, our imagination create the new position of this object, which we call that as image. So when we produce the two light rays backward, the point where these two light rays intersect, that is actually a appearance of the image. And this image is virtual, because this is just our imagination. It is magnified because it is big and larger in size, and it is upright. Like if object head is up, image head will also be up. And it is always the case that when object is between the focus and the lens, the image formed by a convex lens is always a magnifying image. The water waves in a tank travel in a region where the speed of a water wave is faster into a region where it's slow. So we have to draw the position as this is similar, because it slowed down, the wavefront slowed down. If it was moving at the same speed, then we should draw in the same line. If it was traveling faster, it should be ahead. But because I mentioned it is traveling slower, so the distance covered in a slower region will be less, because the wavefronts are moving slow, so they cannot cover too much distance as compared to distance moved in a faster region. So this is how we complete this. On the figure, draw two rays to locate the image. So how to locate an image? First, the parallel light ray from the top of from the tip of the object. Till the center of the lens, it will pass through focus. Then one through the center of the lens will pass straight. The point where the two light rays intersect, if the two light rays intersect by themselves, it means this image is a real image, because it is formed by intersection of the two light rays. So on figure, draw two rays to locate the image of an object and draw the image. Now on figure, draw one another ray from tip. So we have to draw another ray. So what could be the third ray? We will use a ruler, we'll measure the focus here, like example, distance from center to focus, and we'll mark another point, that is focus, F. And then after marking this point, using a ruler, you have to mark this point. Example, this is the focus. So it will continue till the center. So from tip of the object, we'll consider another ray and which passes through the focus. So these are the three light rays. One parallel to principal axis will always pass through focus. Number two, one which is passing through the center of the lens will pass straight, and one which is passing through the focus will go parallel. So these are the three light rays. Even in exam, we need only two to show how the image is formed by a convex lens. Another question related to the lens. A student used a converging lens to produce an image by an object. Figure 8.3 shows 8.3 using a ruler carefully draw the two rays to locate the position of from the object to locate the position of image and use arrow to represent the image. So first parallel light ray from the tip of object, parallel where it will pass through focus. One through the center of the object, tip of the object to the center of the lens will pass straight. The point where the two light rays will intersect or meet, that is the position of image. I can take another ray. Third ray we can also take, but we need only two to represent. So we can take from the ray passing through the focus will go parallel. So that will also intersect at the same point. So, but we need only two of them to draw the image formed by this convex lens. This image will be a real image. It will be inverted, and according to the size, it is small in size compared to object. Figure 6.1 shows a ray of a light incident on a glass block which is having a critical angle of 41. On figure, draw without calculation. So we don't have to do calculation, we just have to sketch. So when I draw the normal here, normal between the surface and the normal, the angle is 90. So out of 90, this one is 30. So remaining angle will be 60. So this angle will be 60. This angle in the glass to air boundary, it is more than the critical because angle of incidence within the glass is 60. Angle of incidence is angle between the normal and the incident. And that is more than the critical. Critical angle is 42. So it will undergo total internal reflection. It means it will bounce back in the same medium. So it will bounce back in the same medium with an angle of 60. Because whenever reflection occurs, angle of incidence and angle of reflection will always be same. Then we draw another imaginary line. So normal 90. Then this angle will be 30. This angle is 30. So angle of incidence now 30, which is less than the critical. So if this angle is less than the critical, then simple refraction will occur. So in simple refraction means light is moving from glass to air. So it bent away from the normal, or speed of the light will increase. So if the angle within the glass is more than critical, light will bounce back. If it is less than critical, it will simple refraction. If it is equal to critical, then like example, if this angle was 41, then it will pass along the boundary. Sound waves travel in air towards the barrier with a small gap as shown. The width of a gap is smaller than the wavelength. So wavelength is when we have a small gap size, draw a pattern of a compression. So we have to draw the pattern of the waves. Why we are drawing in the curved circular wavefront? Because they mentioned that the wavelength is greater than the gap size. When wavelength is more than or equal to gap size, maximum diffraction means we'll draw curve. If wavelength is less than the gap size, then minimum diffraction. So we'll only draw edges a bit curved, but mostly it will be a plane wavefront. Figure 6.1 shows a wavefront approaching a gap. So again, what you have to do, you have to check the measurement, use the ruler, this wavelength and the gap. It appears same. So if it is same, you will show maximum diffraction. Draw three different wavefronts. So one maximum diffraction we have to show. So 1, 2, 3. Then figure 6.2 shows a gap is increased 5 times. The next image. So this gap is increased 5 times. If a gap is larger, small diffraction, how we represent a small diffraction? We draw straight lines. Only the edges will be curved. So this shows small diffraction. And keep one thing in mind, that the distance between the two successive wavefront, that is wavelength, should not change here. So one is a minimum diffraction, another one is a maximum diffraction. The distance between the thin converging lens and the focus is 5 centimeter. We have to label each focus and then find the draw on figure, find the position of object and add object to the diagram. So image is shown, we have to locate an object. Same way we can locate from object to image, image to object. So first we have to mark focus on both sides. 5 boxes equals to 1 centimeter. So this is 1, 2, 3, 4, and 5. So this is 1 centimeter, then 2 centimeter, then 3, 4, 5 centimeters. So that is focus. Here also 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we have to locate the position of object. So the idea is that first two light rays will be there. One is always from tip of the object to the tip of image. That is one light ray. And one is which is parallel will pass through the focus. The distance between the thin converging lens and the object, each focus is marked. We have to label, we have to identify the one which is passing through the focus, because the one which is parallel will pass through the focus. So as you can see, this image appears to be upright. It means the object, this will be a virtual image. Why it will be a virtual image? Because it appears upright. Otherwise, if it was a real image, it should be inverted. So it means object and the image are on the same side, should be on the same side. So object should be here, somewhere within the focus. Because if object is within the focus, then the parallel light ray passes through focus, one through the parallel. So object should be somewhat here. So when we complete the ray, one is from tip of the object to the tip of the image, and the other one, the parallel which is passing through the focus, the ray of a light is there which is parallel and that passes through the focus. So means object should be somewhat here, because if object is here, that is how we draw. The first one, we can draw a parallel light ray from the object. it will pass through the focus. So parallel light ray will pass through focus. One through the center of the lens will pass straight. These two light rays will not intersect. So whenever brain sense the light is coming straight, so whenever brain sense light is coming straight, it will relocate, it will produce these light rays backward. And the position where these two light rays will intersect, that is the position where the image is formed. So that's how we locate it, because always how we identify, because the image is upright. If image is upright, the object, the likely position of object, it is all within the focus and length, between the focus and length. So first parallel light ray passes through focus, one through the center will pass straight. These two light rays will not intersect, so will produce the light rays backward. As a result, it will produce a virtual image. Figure 6.1 shows a diffraction of a wave in a narrow gap. Figure 3 more wavefronts we have to draw. We just have to complete. Using a compass, you will draw 3 wavefront, but keep in mind the wavelength should be same. The wavelength should not change. Then figure 7.1 is drawn. Focal length is 5 centimeter. We have to draw. So how to draw an image by this? So using a ruler, you have to measure. Like example, if I take 5 centimeter, 5 boxes equals to 1 centimeter. So 1, 2, 3, 4, 5. But using a ruler, you have to measure this. So 1. Same thing here. So this is 1 centimeter, then 2, then 3, 4, 5. So this is focus, and 1, so what you will do, the parallel light ray from the tip of the object, parallel light ray will pass through the focus, one through the center will pass straight. So because you can, it's obvious that because the object is between the focus and the lens, so this image, when we observe the object, this won't be real image, it will be always virtual. So when we produce the two light rays backward, the point where the two light rays will intersect, the position where the two light rays intersect, that is the position where the image is formed. So producing them backward will have the image. It should be straight line according to the pattern. So in exam, you will use a ruler, scale, and measure the exact lengths. Another similar question is there. There is an object placed between the lens and the focus. So we have to locate. This is an object in the question. Draw a symbol for eye as well. Label. On figure, draw two rays from top of object, passes through, and use these rays to locate the top of image and label the image, this point as T. So first parallel light ray. The parallel will pass through focus. One through optical center will pass straight. These two light rays never meet. So we will look from this side. And our brain recreate these two light rays backward. So the point, the position where the two light rays will intersect, that is the position where the image will form, and we have to label that point as T. So on figure, another question, the figure 8.1 shows a thin converging lens. Two focuses are mentioned. An object of 2 centimeters position on one of the end of a principal axis. Draw an image, virtual image. So how to get a virtual image? To produce a virtual image, the object must be placed between the focus. So when object is on the focus, one parallel light ray will pass straight, one through the center. That will also pass. And if we look from this side, our brain sense light is coming straight from the object. So our brain relocate these position. As a result, this is the position of image. And this will always be a virtual image. So these are some questions related to image formation as well as ray diagrams and completing the wave motion. Next session, we'll discuss remaining questions from this exercise.